Hey, welcome back to Math with Patrick and Quill. Today's October 24th, and we're solving problem 297 from the Daily Epsilon calendar. And we should show why x matches today's date, so x right here should be 24. So we have a geometry problem, essentially. We're given some information about this angle, it's 60 degrees. This angle right here, it's 84 degrees. This shape right here looks to be a triangle. And then this shape right here looks to be a quadrilateral. So I'm assuming that we have a straight line from these 2 points. This is also a straight line here. So we have the triangle. And then this 84 degrees kind of helps show the angle between these two straight line segments. And so that kind of forms this quadrilateral right here. One thing that we could do with this is learn about some angle relationships based on the quadrilateral and the triangle. Although I already tried this and it didn't work, I at least want to show you why. Let's just call this angle right here, I don't know, angle B, just to assign a variable to it. Looking at the triangle, the 60 and the B and the X should sum up to 180 degrees, just because that is how many degrees you get when you add up the interior angles of a triangle. Then we can also take a look at the quadrilateral. Let's assign maybe A to this one. And then we could do A plus B plus X plus 84 is equal to 360, because that's the number of degrees you would get out of a quadrilateral. And we could actually figure out what A is, in fact, because if we inspect this kind of lower right triangle here, 84 degrees is over on this side, and it looks like we have a linear pair. So 96 degrees would have to go here, 60 degrees is given, and then so we can solve for the third angle. I believe this would be 24, because then all three of those interior angles add up to 180. Then kind of inspecting this point right here, we would essentially have vertical angles. This 24 degrees here would be the same as the 24 there. Oh, and then I was solving for this A number anyways. These are linear pairs here and here. Essentially, A and 24 need to make 180 degrees. So that would make this obtuse angle 156. So I could replace A with actually just the number 156, because it has to be that number for this problem. And then based on what we know about the triangle and the quadrilateral, we are getting two equations and two unknowns, but I'm pretty sure this is just the exact same equation. We could isolate B plus X right here by just subtracting 60. That's going to be 120. If we combine our numbers right here, 156 plus 84 is going to be 240. And then we get the exact same thing. If we subtract both sides by 240, we get B plus X equals 120. And so just studying the triangle and the quadrilateral isn't giving us enough information to solve for X. We only have some kind of relationship between X and another unknown. So we need a different strategy. And I learned this strategy for this problem today. I actually haven't seen this one before. It's the secant angle theorem. A secant is a line that passes twice through a circle. So we have one secant right here and another right there, because it does pass through 2 points. And when two secants form an angle on the outside of a circle, we have a relationship between this angle right here, let's just call it theta, and the two arcs that we're going to find based on our two secants. So this outer arc right here, let me actually color code it, say in green. I'm going to call the major arc because this one is longer. And let's color code the minor arc right here. And these ones are formed, again, by these two secant lines here. And so this kind of larger arc is formed kind of further away from the angle. And then we have this minor arc formed closer to our angle. And the relationship here is the angle should be equal to 1/2 times their difference. And so I'll call this, let's assign some letters. Let's do maybe X, A, B, and C right here. I'm using x just because we have angle x associated with that vertex. But arc XA minus arc BC, and then divided by 2 should be equal to our angle measurement here. I do want to justify like why this even works, and we would have to think about another kind of circle feature here, where if we have some kind of point along our circle and an angle right here, this arc is always going to be twice the interior angle right here. And the way that I kind of like justify it and know that this works in my head is if I take a circle and say I just draw a square in it. So all of these are going to be equal in length. We're all going to have like 90-degree angles everywhere. If I draw a line down the middle, I see that here I have 180 degrees and then here I have 90. And so to me, it kind of makes sense that if I kind of simplify the diagram a little bit, and I notice that this angle here is half of that one, then I could think that maybe if I like grab this point and move it over here, grab that point, move it over there, we would still kind of have the same relationship where this angle right here is going to be twice that one. And then, yeah, this kind of central angle is always going to be equal to our arc's angle on the outside. So there's one feature of circles that I'm like comfy with using, and I can kind of use this idea to then show why this might make some sense. Let's just take this angle x right here and drag it back like a little bit. So I want to drag it back to right here. I want to see if I can get this line segment and the next one I draw to be parallel, because I do want the angle to still be the same. So like something like this is still the angle x. And then you'll notice that on the far side of the circle, I do have a longer arc now. It goes from this point to this point. And on the closer side of the circle, I now have this kind of smaller arc, the minor arc. And interestingly, this minor arc is symmetrical to this other kind of minor arc over here. And my justification here is that these are parallel lines, and so this distance and that distance should be the same because of those parallel lines. And so if we wanted to go from this scenario where we have an external angle and like bring it back to one that's a bit more familiar with the inscribed angle, the central angle, and this arc, we could take the longer arc here. I guess technically not there. Let me actually get the point on the circle. We could take the longer arc from here to here and just subtract off that orange bit, and then we would get the arc that we originally had that's paired up with that angle x. So if we move this angle x backwards, we do introduce these tiny little arcs on both sides of the circle, but since they're the same length, we can subtract them, and we are returning back to just this arc right here that we know is double the angle x. And then lastly, saying that this arc is double the angle is basically the same thing as saying that the angle is half of that arc. So let's use our secant angle theorem and try to solve the problem. We need to figure out what arc XA and arc BC are. However, if we try to look at the given information, this like 84 degrees and a 60 degrees, well, we can't really use a 60 for figuring out the measurements of these arcs because it's like the exterior angle. Actually, that 60 is just supposed to be this one right here. But if we look at the 84 degrees, this inscribed angle right here is subtending the arc XB, not XA, because it goes from the point X there to the point B there. So we could figure out that arc XB is just going to be equal to double its corresponding inscribed angle, and that's going to be 168 degrees. But that's not the one we wanted, right? We wanted XA. Also, where is X going to be in all of our work? Well, we can notice that X is an inscribed angle, and so the measurement of angle X, if we multiply those degrees right there, we should get the length of arc, looks like AC, because angle X subtends arc AC right there. What is kind of convenient, though, is that we do have information about arc XB. So that's from here all the way to point B. And then our variable x has to do with arc AC. And so it's almost like we're double counting arc AB, this tiny one right here. And then if you think about it, so arc XA, if we tack on, arc XA, if we tack on that little arc AB, then we are going to get the whole thing of arc XB. And then if we do the same thing of tacking on arc AB onto arc CB, we get a longer one, right? Arc CA. And the difference between XA, and I guess I should have called that BC to match what I wrote earlier. The difference between these two arcs is going to be the difference between these two ones. We could just, subtract this side of the equation by that side of the equation, and then subtract this by this, and that should be equal, right? Arc XA plus arc AB minus arc BC plus arc AB is going to be the same thing as subtracting arc XB by arc CA. And then the ABs here and here cancel out. So essentially what I wanted to show is that the difference of arcs that we want to be able to use the secant angle theorem is the same thing as these arcs that fortunately we know something about. So let's do a little bit of substitution here. We can replace this difference that we don't know as much about with the one that we do know more about, arc XB minus arc AC. And then we can replace the measure of arc AC with 2x. And we can replace the measure of arc XB with 168. And so let's get that 1/2 there. Let's get that 60 degrees from the formula. And then now, finally, we are just solving for x. So I think the easiest thing to do now is multiply both sides by 2, kind of get rid of this 1/2. 120 is the difference between 168 and 2x. This tells me that 2x needs to be the number 48 so that we can get the difference of 120. And then finally, dividing both sides by 2, we do get 24, and that is today's date. So the secant angle theorem helps us relate all the info on this diagram. X is 24, and we're all done. So thank you for watching. Hope you enjoyed, and I'll see you tomorrow. Bye.